So for number one, what I'm really wanting you to compare is these three molecules. I pointed out the chlorophyll's on there twice. Here, let's do it this way. Okay. So we talked about this on Monday. I've got a luciferin from a dinoflagellate, which we also see right down here. So nice to have a couple different visualizations there. We've got chlorophyll. You should see some things in common there. And we've got hemoglobin. So when I look at them, I see not only do I have some specific shapes in common, and I have some specific elements that are in atoms in common. And those should be jotted down here. That should make sense. But I should also think about the purpose of these things. So when I wrote, why does that make sense? A lot of you said something about, oh, these are the most common elements, or, they all capture oxygen in some way. That's great. Some of you just had the first part. But we want to get to the underlying function. Why am I capturing that oxygen? Why is that important? Why is oxygen toxic? So when you're getting into that makes sense. You want to think back to that story of oxygen. So we've got the luciferin, chlorophyll, and the hemoglobin that are all attaching oxygen to their molecules. In terms of hemoglobin, we know that that is going through respiratory and circulatory systems, delivering it at the cell, using it to make ATP. In terms of chlorophyll, we know that we're putting it in there, the oxygen, and eventually, what is the end product of photosynthesis? What does it need to do? Those things should be similar for a reason. So that's kind of the first thing I want you to look at there. Again, you might have to go back to Monday. Hopefully that kind of makes sense to you. Again, both structure and function, I've got similarities going on there. So here I'm comparing different molecules. Now, if I look back at my chemistry here, there should be one in here, at least, it could be two, that when you look at that first example, you can populate that and go, oh, all right, well, I definitely saw this in particular. So there should be a pretty easy connection to those life principles there. When I look at number two, I'm asking you to do less of a direct molecular comparison, and I'm asking you to compare the reactants versus the products. So first, I'm looking at the firefly luciferin before the reaction, when I get that enzyme, the catalyst protein, and then at the end. So when I look at this actual molecule and this actual molecule, and I think down to the story of what's happening with Lucy and Ace, or I look at this visual over here that sort of nicely shows an analogy of what's actually happening here. So the little O's are the oxygen, and these little what? Pentagons, hexagons? I can't tell how many sides are on there. Those are the luciferase enzymes. Where is that oxygen going? What's happening with that? This before and after is represented a little bit more accurately over here. Now, this is still a bit of an oversimplification because we've got all sorts of reading of the genes, the lux genes, lux meaning light, and synthesizing these proteins and all this other stuff that plays into this that for all intents and purposes we don't need to know about right now. So I look at this molecule, the luciferin. I look at the end, oxyluciferin. Okay, and that also makes sense based on what we talked about right up here. So I see in the beginning a particular shape. But what has changed? If you look at that, you should expect to see exactly what the story told you you should see. Now here in the dinoflagellate, we have a different luciferin than we have in a firefly. But again, if I compare it from the beginning to the end, what do I expect to see? What is the end result here than here? Well, we know that's going to go back to oxygen. So Where is the oxygen attaching? What form is it in? Is it in new molecules? Is it leaving as a byproduct that it's captured in something else? Is it also just attached to the main luciferin in the first place? So we're really just kind of comparing the reactants, the other ingredients it might need, the catalysts, which may or may not be used up. The luciferase isn't. We know catalysts don't get used up, so to speak. And then the end result, the products of that. You'll notice in order to make the reaction happen, different molecules require different things. So you'll see here, I need ATP, O2, the firefly's luciferase, which is the catalyst again, and a magnesium ion. Now, why does that make sense? Well, I've got different luciferin molecules completely, so it makes sense that I perhaps need some slightly different triggers to cause that reaction to happen. Why does that make sense? We'll go back to the operating conditions and think about how these two organisms have very different pressures on them that might explain why their molecular compositions are different. Now, the third part of that, if I compare again this luciferin to this luciferin, that's kind of what I just said, I see a difference in complexity. I see a difference in shape. I see a difference in the little compounds that are attached to the major one. I see, again, those differences in what it needs to cause that reaction. All of those things, again, they can kind of go back to the environment and the evolution of that creature. So that's a little bit of a repeat. Okay, so that's a little bit of help with number one and a little bit of help with number two. Now, again, number two, that should also help you with one of the life's principles in chemistry, especially, again, here I'm looking at the beginning, looking at the middle, I'm looking at the end. One of my life-friendly chemistry examples is talking about sort of what happens at the end of this reaction in particular. Do I have toxins? Do I not have toxins? In this case, we're really focusing on the oxygen, but I'm also thinking about the light. So when we think about the evolution of these organisms, so now I'm kind of getting into both the chemistry and the evolution-based evolve to survive life principles. When I think about the evolution